Welcome to The Explainer. Today, we're diving into one of the most powerful ideas in all of mathematics, differentiation. Now, I know that word might sound a little intimidating, but trust me, by the end of this, you'll see it's actually a beautiful and pretty intuitive concept.
So, let's start with a question. Think about your car's speedometer. It tells you how fast you're going right now. But what does that actually mean? Speed is distance divided by time, right? But in a single frozen instant, zero time has passed, so zero distance has been covered. It's a paradox, and it's a puzzle that basic math just can't solve. But this is the perfect doorway into the world of calculus.
All right, so here's our game plan. First, we're going to explore what we mean by the mathematics of change. Then we'll meet the star of the show, the derivative. After that, we'll build ourselves a handy toolkit of rules, use it to tackle some real problems, and finally, we'll talk about the incredible power we've just tapped into.
At its very heart, calculus is the mathematics of things that don't sit still. It's the language we use to describe a universe in constant motion, whether we're talking about a planet flying through space or the value of a stock changing by the millisecond. It's all about understanding change.
So what is this derivative thing? Well, the best way to think about it is as a kind of universal speedometer. But it's not just for cars. It's a speedometer for any process or function you can dream up. It tells you the precise instantaneous rate of change at any single moment. Okay, time to look under the hood. This is the formal, official definition. And yeah, I know what you're thinking. That looks like a total mess. But don't let all the symbols scare you off. The idea hiding inside this formula is actually incredibly simple.
And here it is, the big secret. All that complicated-looking math boils down to one simple geometric idea: finding the steepness of a curve at a single specific point. You see, for a straight line, the slope never changes. But on a curve, it's different everywhere you look. The derivative is the magic tool that lets us zoom in and find that slope at any instant we choose.
Just a quick heads up, you're going to see the derivative written in a few different ways. You'll see this f prime of x, which we say as f prime of x, and you'll see dy over dx. They might look different, but don't let it throw you. They all mean the exact same thing. All right, now for the fun part. We're not going to just memorize a boring list of rules. Think of this next section as us assembling a powerful toolkit. With just a few basic tools, you'll be ready to handle a huge range of problems.
And what's so cool is how simple these basic building blocks are. The derivative of any constant number is just zero. Which, that makes sense, right? A constant, by definition, doesn't change. And the real workhorse here, the one you'll use all the time, is the power rule. These are the absolute basics for everything else we're going to do.
So let's put our new toolkit to the test. We've got a pretty standard polynomial here. The beauty of this is we can just go through and handle it piece by piece. We apply that power rule to each term one at a time. And that -8 on the end? Well, it's a constant, so its derivative is 0. It just vanishes. See? It's that straightforward. Okay, time to level up. What happens when you've got two functions being multiplied together? Well, you can't just find the derivative of each one separately. Nope. For that, you need a special tool, the product rule. It looks a little weird at first, but it's just a pattern. Derivative of the first part times the second part, plus the first part times the derivative of the second. Let's see it in action. It's a perfect example of the process. We just label the first chunk u and the second chunk v. Find their derivatives on their own, that's u prime and v prime, and then you just plug everything into the formula. It's really just like following a recipe. And now for the big one, the chain rule. This is your go-to tool when you have a function inside of another function, kind of like those Russian nesting dolls. And the rule itself is actually really elegant. You take the derivative of the outer function first, and you leave the inside alone, then you multiply all that by the derivative of the inner function. Check this out. The outside function here is basically something to the power of 4. The inside function is that whole polynomial. So first, we deal with the outside using our power rule. We bring that 4 down. Then we multiply that by the derivative of what was on the inside. We literally just chain them together. It's perfect. Okay, so we've built our toolkit. Now it's time for the payoff. Let's see what kinds of awesome real-world problems we can actually solve with this stuff. This is where all that theory smashes into reality. And I mean it when I say this stuff is everywhere. In physics, it's the absolute foundation of how we describe velocity and acceleration. In business, it's how companies find the exact point to maximize profit. And in computer science, oh yeah, it's the engine that drives so much of modern artificial intelligence and machine learning. Let's get really specific with an example. Imagine this function, s of t, tells you an object's position at any time t. If you want to know its velocity, how fast it's going, you just take the derivative. We apply our simple power rule to each little piece, and poof, we have a brand new function that gives us the velocity at any moment.
And this brings us completely full circle. Remember that very first question we asked? Finding speed in a single instant seemed impossible. But now, with our velocity function, we can ask a super specific question. What is the exact velocity when the clock hits 2 seconds?
All we have to do is take that number 2 and plug it into our velocity function. The result is -8. That's it. That is the instantaneous velocity. We've solved the paradox. And that negative sign? It just means the object is moving in the opposite direction at that specific moment. Simple as that.
So as we start to wrap things up, let's just take a step back and appreciate what we've uncovered here, and maybe get a quick glimpse of where this can all lead.
Look, the really crucial thing to take away from this is that we've just learned the basic grammar for the language of change. This isn't just a bunch of abstract formulas. It's a way to precisely describe and even predict how things work in a world that is constantly in motion.
And believe me, this is just scratching the surface. The toolkit we put together today is the foundation for way more advanced stuff, like something called L'Hopital's rule, which lets you solve problems that seem totally impossible at first glance. The rabbit hole goes so much deeper.
So we'll leave you with this final thought. We've seen that calculus gives us this incredible toolbox for modeling change in the world. And it doesn't matter if your passion is science or economics or art or technology, the principles are the same. So the real question is, what change will you model?